Okay, well, we're going to carry on with our model selection session. We've done best subset selection. Now we're going to do forward stepwise selection. So best subset is quite aggressive, looking at all possible subsets. Forward stepwise is a greedy algorithm. Each time it includes the next best variable, but it produces a nested sequence. So it's a much less adventurous search. It keeps a nested sequence of models each time you just add the variable that improves the fit the most. So we also back using our markdown formatting, and so we'll continue with that. So let's have a look at the screen. And we've got our heading, forward stepwise selection, and we're back using reg subsets. And it's the same function that did best subsets, but yeah, we tell it method equals forward, and we also want the number of variables. We want to use the full number of variables, which is 19. And so that's really fast as well. And there's a summary for that, just as there was for the best subsets. And now this one, if you look through the models that were selected, you'll find that they exactly nested. So each new model includes all the variables that were before plus one new one. And so if you study that, you'll discover that. And we can plot the CP statistic. I beg your pardon, we make the plot for this model, the schematic plot like we did before, and it looks very similar to what we saw for best subsets. Different in some places, but the same kind of structure near the good end, which is the low CP end, where there's a consistent group of variables that are in, a little bit of fluctuation down at this end over here in terms of which of those variables are in. Okay, so we've got best subset and forward stepwise, and we can select the models using CP. There's also adjusted R squared and BIC. But here we're going to actually use a validation set. So what we're going to do is we're going to pick a subset of the observations and put them aside and use them as a validation set and the other as a training data set. So let's see how we might do that. And this is a little different to the way we do it in the book. And so first of all, we see the dimension of hitters. There's 263 rows. So we're going to roughly go for 2/3 training and 1/3 test. And approximately 2/3 training is 180 observations. And so that's what we'll do. And just for reproducibility, we'll set the random number seed. And you can set it to any number. We set it to 1, doesn't matter. Well, it does matter, but for our purposes, we're not particular. Okay, so here we go. There's a command here. First of all, inside, sequence 263 creates SEQ 263. It just creates the numbers 1, 2, 3, 4 up to 263. So it's a shortcut for doing that. Okay, and here we're using the sample command. So we're going to sample from that sequence. We're going to take a sample of size 180, and we're going to say replace equals false. So this will sample 180 indexes of observations. Okay, and let's just look at them. Well, there they are. There's 180 numbers chosen at random from the sequence 1 to 263. So those we're going to use, that set of index, those rows we're going to use for our fit-in. So regfit.forward now, we run reg subsets again, and everything's the same as before, except now we tell it to use the data frame hitters, but indexed by the rows in train. Okay, and so that'll use this subset of data. Okay, so that's fit the model. Now we're going to work out the validation errors on the remainder of the data. So we know there's 19 subset models because there are 19 variables. So we'll set up a vector having 19 slots, and we'll make a X matrix corresponding to our validation data set. So here we use the model matrix because we want to use the formula that we used in building the model, which was celery twiddle dot, which means model celery as a function of all the other variables in the hitters data frame. But celery is a response. And so we put that formula, we give that as an argument to model matrix, and we tell it that the data it should use is hitters, but now rather than indexing by train, we index by minus train, which is a really nice device in R for excluding the observations indexed by train. So that just leaves a remainder. So that's a negative index set. Okay, so we build that test model matrix, and now we're going to make our predictions for each model. So we go in a loop for I equals 1 to 19. We use a coef function to extract the coefficients for the model of size ID equals I. So I is going to index the size, and we go in a loop and do it for each size. And now, the unfortunate thing, there's not a predict method for reg subsets, which would have been handy. So we basically got to do it all ourselves. And so the coefficient vector that comes back, if we look at it, well, we can't yet because we're in a loop. It's just got the subset of variables that are used in that model. And so to get the right elements of X test, we have to index the names of that, index the columns by the names that are on the coefficient vector, right? So that's one way of doing that. So that's the subset of columns of X test that correspond to the variables that are in this current coefficient vector. And then we do a matrix multiply by the coefficient vector. So it's a little bit of a loaded line. And then having got the predictions, so that gives the predictions, and then we compute the mean squared error. So there's the hitters dollar salary minus train, minus the predictions, square it and take the mean and put that in validation errors. And that's the end of our loop. Okay, so that worked pretty quickly. And then we're going to plot the root mean squared error. So we plot that in a plot, and there we have it. So that's a validation error. It's slightly jumpy, which is okay. I mean, these are data. There's only, there's less than 90 observations in the validation set, so there's going to be a bit of noise. But there seems to be a minimum here around 5. The 10 that we chose before is a little bit higher than the minimum. We may as well put the residual sum of squares for the model on the same plot. So notice we remove the first one. This corresponds to the null model, which was not included in our validation plot here. And so there's the residual sum of squares. And notice, of course, as it must do, the residual sum of this is the root mean residual sum of squares. It's monotone decreasing, as it has to be, because forward stepwise, each time includes a variable that improves the fit the most. And so therefore, by definition, it's got to improve the residual sum of squares on the training data. Okay. And we may as well annotate our plot with a legend. It's very easy to do. We tell the legend command to put the legend in the top right corner. We give it the legend and a few more details. We tell it well, let's just do it and see it. And you see in the command how we achieved that. I use PCH, plotting character 19, quite often. It gives you a solid dot, which is often nicer to visualize on the screen, especially if you're doing it in color. And so this was a little tedious. We had to write our own, basically, method. We had to write code for doing the prediction. We're going to use we will make predictions from reg subsets model in the future. So we're going to end the session by actually just writing a function for doing that. And we often do this in R. When we find ourselves repeating code that's tedious, we write a little function to do it for ourselves. So we this is actually writing a method for for a reg subsets object. So predict.reg subsets. And we give it argument object. That's going to be the reg subsets object that we want to predict from. We give it new data and ID, which is going to be the ID of the model. It's slightly technical, but not too hard to understand. A reg subsets object's got a component called a call, and that's the call that was used to create it. And part of the call is the formula, and so we can extract that formula through this little incantation here. And then using the formula, we make a model matrix from it, much like we did before. Then we extract the coefficient and do the matrix multiply. And so we put that all together in a function, which we'll just enter into our session now. And so now that function's defined, and it'll be ready for us to use in the next session, where we're going to actually use cross-validation.